Today we'll be doing the integral from 0 to pi over 2 of the square root of tangent of x dx. And to start off, we will make a substitution. So we'll let y equal the square root of the tangent of x, which means that y squared equals the tangent of x. And solving for x, we have x equals the arctangent of y squared. And that means that dx equals 1 over 1 plus y squared, and the derivative of y squared is 2y. So we have dx equals 2y over 1 plus y to the fourth, and the bounds of integration, y1 will be 0 and y2 will be positive infinity. So it's equal to the integral from 0 to infinity of y times 2y over 1 plus y to the fourth dy, which is twice the integral from 0 to infinity y squared over 1 plus y to the fourth dy. And now all that's left is to solve this integral, and we will construct a function g of z, which is z squared over 1 plus z to the fourth, and z to the fourth plus 1 equals 0 when z1 is e to the I pi over 4 and z2 equals e to the I 3 pi over 4. There will be two extra ones, but we don't have to worry about these in this scenario. And we'll construct a contour C, which will go from minus r to r, union a semicircular arc. And what this looks like will end up being, so we have minus r to r, and it's going to be connected like this, and it loops back around like this, which is the arc. So this will be CR, and this is the contour. And like I said, there would be 4 singularities, but only 2 are enclosed in this contour, so we don't have to worry about these 2, but we do have to worry about these 2. This will be our Z1 and our Z2, and it makes an angle of pi over 4. So now from here we have to construct our contour integral, and it will end up being the integral along this closed contour of z squared over 1 plus z to the fourth dz is the limit as r tends to positive infinity of negative r, the integral from minus r to r of y squared over 1 plus y to the fourth dy, and then plus the integral from minus, no, not minus, it will be the integral of along the semicircular arc of z squared over 1 plus z to the fourth dz. But as r tends towards positive infinity, this will end up going to 0. So we have the integral along this contour of z squared over 1 plus z to the fourth dz will equal the integral from minus infinity to infinity of y squared over 1 plus y to the fourth dy. But since the function is even, we could write this as twice the integral from 0 to infinity of y squared over 1 plus y to the fourth dy, which is exactly the integral we're looking for. Now all that's left is to solve this contour integral. So using the residue theorem, we have this is equal to 2 pi I, the residue of z squared over 1 plus z to the fourth at the poles, which I mentioned was z1 is e to the I pi over 4 and z2 is e to the I 3 pi over 4. And since these are simple poles, I could take the derivative of the denominator. So you have I equals 2 pi I, the residue of z squared over 4z cubed at z1 equals e to the I pi over 4 and z2 equals e to the I 3 pi over 4. So we're going to have our integral is 2 pi I over 4. The residue of z squared over z cubed. z1 is e to the I pi over 4. And z2 is e to the I 3 pi over 4. 2 pi I over 4 will simplify into pi I over 2. We have the residue of, this will turn into 1 over z. And z1 is e to the I pi over 4. z2 is e to the I 3 pi over 4. So now all that's left is to evaluate the limit and sum these residues up. So you have the integral is pi I over 2, and then the limit as z approaches e to the I pi over 4 of 1 over z, and then plus the limit as z approaches e to the I 3 pi over 4 of 1 over z. So we have the integral is pi I over 2. This will end up being 1 over e to the I pi over 4, and then plus 1 over e to the I 3 pi over 4, which can be simplified into pi I over 2 e to the minus I pi over 4 plus e to the minus I 3 pi over 4. And to evaluate this, we'll use Euler's formula. So decompose this into a sum of cosines and sines. So this is equal to pi I over 2, the cosine of minus pi over 4, plus I sine of minus pi over 4, and plus the cosine of negative 3 pi over 4, plus I sine of negative 3 pi over 4. So this is equal to pi I over 2, and cosine is an even function, so this will end up being the cosine of pi over 4. And we also know that the sine is an odd function, so we could put the negative towards the front. So minus I sine pi over 4 plus the cosine of 3 pi over 4, and then minus I sine 3 pi over 4. This is equal to pi I over 2. The cosine of pi over 4 is the square root of 2 over 2, minus the sine of pi over 4 is the square root of 2 over 2, plus the cosine of 3 pi over 4 will be negative square root of 2 over 2, minus the sine of 3 pi over 4 will be positive the square root of 2 over 2. So as you can see, these real parts will end up canceling. We have pi I over 2, negative I square root of 2 over 2, and then minus I square root of 2 over 2, which simplifies into pi I over 2, negative 2I root 2 over 2, but the 2's will end up canceling. So we have a pi I over 2, negative I root 2, which is a negative pi I squared, square root of 2 over 2, which is negative pi I squared. We know it's negative 1, so times negative 1 square root of 2 over 2, which is equal to pi square root of 2 over 2. So now we could say that, therefore, the integral from 0 to pi over 2 of the square root of the tangent of x dx is equal to pi times the square root of 2 over 2. And so this is the final result. Thank you very much for watching.